Alright, so today is day number 4 on the Lagrange Taylor series error. Before I get into that, I'd like to talk about another type of error that we've seen and then show the relationship of those two. So let's jump into it. Okay, so let's find the Maclaurin series, degree 6, for y equals cosine of x. Alright, so I'm not going to go through how we found this, but we should be, at this point, pretty good with this. So here's the degree 6 Maclaurin series for y equals cosine x. Let's use this series to estimate the value of cosine of pi over 6. So I would go ahead and take this polynomial that's been represented here, and I would just plug in a pi over 6. So I would get 1 minus pi over 6 squared over 2 factorial plus pi over 6 to the 4th over 4 factorial minus pi over 6 to the 6th over 6 factorial. And of course we'd use our calculator here. And what we get here for an estimate is 0.866. Now it goes out a little bit further, but I'm going to stop there. Now, of course, pi over 6 is pretty close to 0, which is the center of this Maclaurin series, or this Taylor series, right? So a Maclaurin series is centered at x equals 0. The further we get away, so if we tried cosine of, I don't know, pi over 3, it would be a little less accurate, and a little less accurate from there. Now, how do we determine an upper bound on the error, right? If we want to try to maximize our potential error, therefore kind of covering our bases on that, in this case, we like it, right? Because cosine, its power series representation, this Maclaurin series, right, is alternating in nature. So in order to use the alternating series error, we need to know two things. We need to know, one, is the limit as n goes to infinity of the sequence equal to 0. Clearly, as we look at this sequence up here, clearly it's going to 0, right? And 2 is each term decreasing, okay? So decreasing, and clearly that's true as well. So what we know about the alternating series then is to find its error, we just take the absolute value of the next term. All right, so the absolute value of the next term would be the absolute value of x to the 8th over 8 factorial. So if I plug in pi over 6, take it to the 8th over 8 factorial, that'll be positive. It's the positive term in that alternating series, but absolute value of that, we would get a really, really small number, and it's 1.40109. My calculator gives me this, times 10 to the negative 7th. Wow, look at how close that is to the actual. And you have to go out a number of decimals further than this. When your calculator, you actually type in cosine of pi over 6, you have to go out like 3 or 4 more decimals in order to get a number that's different than what you'd get using this Maclaurin series. So that's great, right? Every time you see an alternating series, you should say, that's awesome. I know I just take the absolute value of the next term. But how do we calculate error if the series doesn't alternate? And that's what we're getting into today. That's the Lagrange error bound. And what the Lagrange error bound will do is it's going to give you an upper estimate of the error in order to kind of, how shall I say, cover your bases again, right? Just in case, right? We're going to go with the highest possible error. Now, it could be less than that. It could be even close to 0, like very close to 0, but we're going to go with the upper estimate. So let's move on to the next slide. All right, this slide is kind of busy. All right, but let p sub n of x be the nth degree Taylor polynomial for f of x centered at a, right? So this right here should look very familiar, right? Nth degree polynomial, that's its highest degree. So how do we then come up with how far off that is? What is the error on that? Well, let's imagine that I've got all these terms. Well, what would be left over is this error of those n terms, okay? And this is how we define that remainder. And there's a lot of stuff going on here, but I'm going to try to make it as simple as possible here. This actually looks very familiar, right? This is the n plus 1th derivative, so in this case, the error of the first 4 terms evaluated at some value x, right, which we'll talk about in a moment, is going to be the 5th derivative at some point, I'll explain what that is in a minute, times x minus a to the n plus 1th power over n plus 1 factorial. So you might be asking yourself, how's that any different than the next term, kind of like it was with the alternating series? It's really not that different. The only thing that's different is z. And what z is a value between a and c. What are a and c? Well, a and c are the center of our polynomial and the value we're approximating at. Okay, this should be a c right here. Okay, so what we're going to do is we're basically just going to test this with a, and then we're going to test it again with c, and we're going to see which one is bigger. That's it. Okay, that's that value z. Okay, so z is just the value between a and c such that the remainder is maximized. So let's go ahead and try it on an example. Alright, so let's use a 4th degree Taylor polynomial for natural log of x to approximate the value of 1.2, natural log of 1.2, and determine the error of approximation. So the degree will be 4. That'll be a 4th degree polynomial of natural log of x. So f prime of x would be 1 over x. F double prime of x would be negative 1 over x squared. F triple prime of x would be positive 2 over x to the 3rd. The 4th derivative would be negative 6 over x to the 4th. And then we would get 24 over x to the 5th. Now it's not asking us to build the polynomial. Actually, maybe it is. Let's see. Use the 4th degree polynomial for natural log of x to approximate the value of natural log of 1.2. I'm not going to do that here. All I'm going to do on this slide for this purpose, you would build the polynomial, right? So you could go ahead and figure that out on the side, but I want to find out the error, okay? So a is the center, and the center here is going to be 1. C is the approximation for x, so we're plugging in 1.2. Therefore, z would be somewhere between 1 and 1.2. Okay, so what I'm going to do is I'm going to look over here. So the error of the 4th degree polynomial evaluated at 1.2 will be the absolute value, or the absolute value of that error will be less than or equal to the 5th derivative at z times x minus a. Okay, x minus a was the center, which is 1, to the 5th power over 5 factorial. Now you might be wondering, well, what do I do from here? I don't understand x or z. What's the difference between the two? Okay, so I'm going to test this in 2 different ways. So the error of this output is going to be less than or equal to the 5th derivative, 1.2 minus 1 to the 5th power over 5 factorial. And I'm going to test 2 different numbers here. I'm going to test the number 1, and then after that I'm going to test the number 1.2. And I'm going to figure out which of those comes out to be larger. Okay, so let me walk you through what I've got here. So I plugged in 1 into the fifth derivative, which was 24 over x to the fifth. So 24 over 1 to the fifth times 0.2, which is just 1.2 minus 1 to the fifth. And I came out with this value here, where the error of this would be less than or equal to that. Okay, and then I did the same thing with 1.2 and came out with this. Now I'm going to take the larger of the two errors. So I would approximate the error of what I would come up with. Right, of what I would come up with if I did the sixth degree Taylor polynomial of this, or excuse me, fourth degree Taylor polynomial of that with 1.2 plugged in. Right, that would come out to be this close to the actual. Okay, so again, take the larger of the two just to cover your bases and make sure that you know, we want to over approximate our error. Therefore, then we've done the Lagrange error bound. So we'll do some more practice in class, but this is the basics of how to find the error of a non-alternating series. And there you have it. Have a nice day.